This lecture is an introduction to the concept of force and how it is related to the acceleration of objects. Force is any push or pull. It is an attempt to change the motion of an object or to change its form. Now, an emphasis here is on the word attempt. Forces do not always cause a change of motion or form because they may be opposed by other forces. If you'll recall the definition of acceleration, it's a change in velocity over time. And velocity, as you'll recall, includes both speed and direction. So any change in speed or any change in direction results in an acceleration. We believe that the cause of any acceleration is a force. More specifically, it's a combination of forces or a net force that causes an object to accelerate. So acceleration depends on the net force applied to an object because more than one force can be acting simultaneously. So to change the motion of an object, you must change the net force acting on it. Here's a hockey puck. When this hockey puck is at rest, the net force on it is 0. Gravity is pulling down, the ice is pushing back up, the puck is not moving relative to the ice, so the puck is in equilibrium. But if you hit the puck, in other words, you apply an unbalanced force to it, then the puck experiences a change in motion. It accelerates. If you hit it differently, it accelerates differently. So if you push or pull on any given object with a set of forces, what you'll find is the larger the net force, the more the object will accelerate. In other words, there is a direct proportionality or relationship between force and acceleration. We could symbolize it like this. Acceleration is directly proportional to the net force. That alpha symbol is our symbol for proportional. Consider this situation. You're pushing an empty shopping cart with a given force. Now, push that same shopping cart when it's heavily loaded. If you push it equally with the same force in both cases, you'll see that the empty shopping cart accelerates much faster than the full cart. The loaded shopping cart will not accelerate as much. What this shows is that for a given force, if we push equally, the acceleration of an object depends on its mass. But that dependence is inverse. In other words, if you push with the same force, but you have twice the mass to push, that will result in only half the acceleration. So the acceleration is inversely proportional to the mass. We could show it in equation form like this. The acceleration is proportional to 1 over the mass. Inversely means that the two values change in opposite directions. If mass goes up and it's in the denominator, then the acceleration goes down. So far we've seen that acceleration is directly proportional to net force applied to an object, and acceleration is inversely related to the mass of the object. You can actually combine these two proportionalities into a single equation. It's actually not an equation yet, but a single proportionality will say acceleration is proportional to the net force over the mass. Now, anytime you have a proportionality like this, acceleration is proportional to net force over mass, you want to try to change it into an actual equation so you can apply it more broadly and more specifically. This particular proportionality is known as Newton's second law of motion. We could say in words like this. Newton's second law says the acceleration produced by a net force on an object is directly proportional to the size of the net force, it's in the same direction as the net force, and it's inversely proportional to the mass of the object. But as I said, even though that gives us a qualitative idea of what will happen if you change any one of the variables, it would be better if we could find an actual equality, an equation that would tell us exactly what to expect. In order to change a proportionality into an equation, we need a constant, or more particularly, it's called a constant of proportionality. We usually just drop those last couple of words. It turns out, in this case, the constant is simply the number 1. How is that? Well, if you do a series of experiments where you keep acceleration constant and you graph the results of finding out if for a given force what mass it would require to give a result of the same acceleration each time, the slope of that line would simply be 1. So the acceleration is equal to the net force divided by the mass. This is an equation that represents Newton's second law of motion. It can tell us for any 2 of those variables, we can find out what the third is. If you look at that equation, since the constant is simply 1, you can predict things like if the net force doubles, then the acceleration doubles, because they are directly proportional. If the mass is doubled, the acceleration will be halved, because they are inversely related. If you doubled both the force and the mass, then the acceleration would actually be the same. You would have 2 times the force on top, but 2 times the mass on bottom. The 2's would simply cancel each other out. So if acceleration equals net force over mass, and we wanted to rearrange that equation to solve for force, then the equation would look like this. Net force equals mass times acceleration. You can write the acceleration times the mass. It doesn't matter which order you put those 2 variables in. Now, if you asked, what is the net force acting on a 1 kilogram object if it is accelerating at 1 meter per second squared, and apply it to that equation, then you would find that 1 kilogram times 1 meter per second squared simply equals 1 kilogram meter per second squared. The units do not cancel out. In fact, this is a complex combination of 3 measurement units. Mass is measured by kilograms, distance or displacement is measured by meters, and time is measured by seconds, and it appears twice in the equation, and so we get seconds squared. Rather than always writing a complex set of units, scientists often simplify by just defining a new unit of measurement. In this case, 1 kilogram meter per second squared is defined as the Newton. Whenever you have a unit of measurement, it is not a proper noun, and so you don't capitalize it. If you were talking about Sir Isaac Newton, you would capitalize the name and put a capital N there. But when you're talking about the unit, you use a lowercase. On the other hand, whenever you abbreviate something that was named after somebody, it is usually the case that you will capitalize that letter. So we have a capital N whenever we abbreviate. So 1 Newton equals 1 kilogram times meter per second squared. So what this means is that you have to recognize that anytime you see that capital N or the word Newton, that is actually a combination of 3 other units. This is just something that you have to know and remember. 1 Newton equals 1 kilogram meter per second squared. Now if we go back to the original equation, we could use symbols instead of writing out all the words. So this is the equation that represents Newton's second law, but we could symbolize it with whatever letters we choose. Typically, these are the letters that I will use. A lowercase a will stand for acceleration, a capital F will stand for the net force, and m will stand for the mass, a lowercase m. We can put that into our magic equation triangle like this. If you draw your triangle, separate it with the T-bar in the middle, we see that the F is on top, and therefore it has to go in the top box of the triangle. That leaves the A and the M, and you can put them in any order. I'll stick them in the same order that we see them on the screen, left and right, A and M. With the magic equation triangle, now if we know any 2 variables, we can solve for the third very easily. So let's do a few math problems. Here's a car with a mass of 1,000 kilograms. What is its acceleration if the net force is 2,000 newtons? It's always a good idea to write down everything, including your magic equation triangle. So there it is in the top part of the screen. And now let's write out what we know. Mass is 1,000 kg. Notice I don't just write 1,000. I write m equals 1000 kg. Write it all out. Slow down and write it down, and you'll always get these problems correct. What is the acceleration produced by a net force of 2,000 newtons? That means F equals 2,000 N. A, acceleration, is what we need to find out. Now what I like to do with my magic equation triangle is put my thumb over the variable I'm trying to solve for. So I take the A out of the equation and write it down, and then put my thumb over it. There's my thumb. I'm left with F over M, so there's my equation that I need for this particular problem. Substitute 2,000 newtons over 1,000 kilograms. Now I could just stop and solve this right now. I would get 2 newtons divided by kilograms, but I don't know what a newton divided by a kilogram is. That does not sound like an acceleration unit. I need something like meters per second squared. But if I remember that the newton is a kilogram meter per second squared, now it will make more sense. I can see that the kilograms on top and bottom will cancel, and I'm left with 2 meters per second squared. And so my answer is 2 meters per second squared. Now if we have that same car, but the force is increased to 4,000 newtons, what is the acceleration? Well, we'd solve it the same way. Let's write down what we know. Mass is 1,000 kilograms. Force is 4,000 newtons. Acceleration equals question mark. We're obviously going to use the same equation, plug in the same set of numbers, except that it's a 4,000 instead of a 2,000 for force. We'll get 4 meters per second squared. Now, if you recall, the last answer was 2 meters per second squared. I hope you understand that what we're saying here is anytime you double the force, you double the acceleration. This is a specific case, but we can generalize from it. If a car can accelerate at 2 meters per second squared, what acceleration can it attain if it is towing another car of equal mass? In other words, what this question is asking, what happens if you double the mass? Again, we look at our magic equation triangle, we pull out the equation for acceleration, and what we're saying is, instead of m, we'd have m plus m, or 2m. Well, the only way that we could solve this is to either have numbers or just to puzzle it out. If you have a 2 in the denominator on the right side, your math teacher has taught you that whatever you do to the right, you have to do to the left. So we have to put a 2 in the denominator on the left. So that would be A over 2 or 1/2 times A. In other words, if the car can accelerate at 2 meters per second squared, but then you double the mass, you split that acceleration by 2 and change it to 1 meter per second squared. Let's do one last problem. How much force, or thrust to use a better term since we're talking about an airplane here, how much force must a 30,000 kilogram jet plane use to achieve an acceleration of 1.5 meters per second squared? Let's write down what we know. The 30,000 kilograms is actually a mass, so we put m equals 30,000 kilograms, and the 1.5 meters per second squared is an acceleration. So what we're trying to find this time is the force. If we take the F out of the equation of the triangle and put our thumb over it, we see A beside M. We can write that in any order. It's traditional to write M times A because the units then will become kilogram meter per second squared. So F equals M times A equals 30,000 kilograms times 1.5 meters per second squared. That equals 45,000 kilogram meters per second squared, or we could change that to 45,000 newtons, and that would be our final answer. So, are you ready to do some problems involving Newton's second law? I think so. Check the Google Classroom for a set of homework problems.